So welcome to another video. This particular video is going to be regarding the polarization index simulators that I build up to test the MTR 105 out. I needed to build up a unit with a higher resistance range rather than the original unit that I had, which you see on the right there, which is basically a simulation of a three-phase motor. It has 3 windings built into it and a simulated polarization index circuit between each winding and earth, and I've also developed it later on to have leakage between each of the windings, which are the 3 connections that you see at the end of the case there, and that then adds a further testing element to the design. So the one I've built up to work with the MTR 105 is on the left there. Take the one out of the way, and this one, you can see they're quite basic inside. I'll put up the schematic diagram along with the parts list as well, and it's basically a capacitor charging circuit with a fixed resistor across the capacitor to give the end resistance that I'm looking for. So the RC circuit is this part built in down here. This is the C1, which is made up out of this one for 2 capacitors, and this is my R1, which is actually 3 resistors, and then R2 is just on the bottom here, gives the RC time constant with the capacitors. I try and keep the RC constant somewhere between about 80 to 120. That gives me the maximum resistance value stored around about 6 minutes through the polarization index test, which produces the kind of curve that I like to see. In combination with that, there's the resistance ratio between R1 and R2 that also affects the circuit, and I keep that around about 10 to 15, and then that kind of produces the curve that I like to see from this kind of test that I'm doing.
Okay, so the time constant worked out by the nominal resistance and capacitance values isn't quite right for this circuit because it's a more complex circuit than that. So to work it out completely theoretically, you have to calculate the Thevenin equivalence, and that's what I've done in this little table and the diagram here. This is the equivalent Thevenin circuit here with the final resistance, supply voltage and the capacitance. These values are then utilized within the standard formula for calculating the charge in a capacitor, and that's shown up in this column here. I can then work back from them until I end up with the output current from the insulation tester, and hence I can then calculate what the resistance value will be displayed on the insulation tester, and that's the values in this end column here. And then I can work out nominal DAR and pi values as well, and I'll be able to compare these values to the results obtained when I test it with the insulation tester. Okay, so back to the actual simulator itself.
The inductor you see here on the left, that's just something else that I add in. I use a lot of micro ohm meters, or we call them ductors in the UK, and put in an inductor into the circuit gives me another testing element for this box. With, in actual fact, with the MTR 105, I'll be able to measure the inductance and the DC resistance of this, which gives me a couple of more test points for that unit. For the ductors that I use, that will just give me a DC winding resistance to measure. But these are quite beefy, so the micrometers kick out about 10 amps, and this will obviously take that, no problems. So I'll assemble the unit up, and then I will demo a micrometer test, and I'll demo a polarization index test on it as well. This particular unit can actually take up to 5,000 volts, so I'll test that with a different tester than the MTR 105 that can put out the higher voltage levels. Okay, we're set up with a micro ohm meter. This particular unit is the Chevanarnu CA6250, so it's just a 4-wire resistance measurement really. There's the 2 Kelvin clips that are connected to the test set, one to one side of the coil inside and the one to the other side of the coil. Okay, so set up onto the screen a bit better. All I have to do is press the go button. That's a pulse measurement, gives me the value there, 33.68 milliohms. Okay, so that's that one done. What I'll now do is I'll set up an insulation tester and I'll go for a polarization index test on the unit and see how that comes out. This is the Fluke 1555 insulation tester I'm using. Will go up to 10 kV, but I'm only taking this up to 5 kV. Otherwise the capacitors will not like it. I'll change it to polarization index test there. And my voltage is 5 kV. And we hit the go button. And you can see with this instrument I've got a timer on the right there, main display showing the resistance reading, and in the bottom left I've got the current being tested. So for a polarization index test, I record, for the first minute I'll record the reading every 15 seconds, and then after that I'll record it every minute. I'll either cut out a chunk in the video of the main test, or I'll speed it up so it's not the full 10 minutes, because that would be a rather depressing video, I think. Although that might be me being a little bit biased after the thousands of tests that I've done. So with the test set up, you can see I've actually, because I'm going to be testing at 5,000 volts, there is a danger that you can get leakage between the test leads at such a high voltage. This instrument from Fluke does have a guard terminal, but they don't supply shielded test leads with it. So I've deliberately configured the test so that the leads are well away from one another. You can see the black lead from the negative is coming around this way, and the red lead is over the other side, well and truly out the way of each other, so there shouldn't be any leakage between those two leads. I do have a set of test leads that are shielded, but the connections on these, you can see they're quite long, and the test connectors on those leads are not compatible with this test set. So just while the test is going on, for interest, this is a set of shielded test leads. The positive lead is actually a fairly standard lead, but the negative lead here, you can see, has the shield around it, which is this green wire that's underneath. Flip it over is best actually. That's this green wire here, and there's a shield running all the way up this lead, so if there's any leakage between this lead into this lead, it will hit the shield first. The shield will take it into the guard terminal of the insulation tester, and the insulation tester will ignore that leakage current and remove it from the overall reading. And as you can see, this jack here is not compatible. This is the guard lead that comes with the Fluke instrument, and you see they're just not compatible. This won't plug into the Fluke, so I can't use shielded test leads with that. The setup for the Fluke is actually to use the guarded test lead as part of the test setup. So if you're doing a three-phase winding, you can connect the guard to either the frame or one of the other windings that's not under test, and you can get a true reading of the leakage either down to earth and not via the other windings, or the leakage from one winding to another winding and not via the earth path. It adds to the diagnostics you can do with an insulation tester. Okay, coming up to the last 30 seconds of the test. 13.7 gigs at the moment. Okay, so 13.8 gigohms for a final reading. Pi was 6.28. Okay, so that's the final reading. I hit the enter button. I will store this. It gives me a tag name then, and what I can actually do is show those results. Tag 1, there's tag 3, there's my result there, and then I can then page through relevant readings. Gives me an initial setup. There's the test voltage was 5266 volts, capacitance it didn't find anything, PI was 6.28. It does, at the same time as it does PI, it does do the DAR as well, which is a very nice feature. And then it gives me the current, that'll be at 10 minutes. So what I will do as well is download the test results onto the computer, and then you'll see what the Fluke Forms collects from the instrument. My version of this tester is very, very old, so it never came with the Bluetooth adapter. I do have a Bluetooth adapter for it, but I've never been able to get it to actually work, so I can't collect the data live as you're doing the test.
So what you see in front of you here is the PDF file created from the Fluke Forms from the readings that I've downloaded from the 155 insulation tester. You can see I did 6 tests overall. I started off at a 5 kV PI test, then dropped back down to 250, then the 500, 1 kV and 2.5 kV test voltages. And then I finished off with a final 5 kV test again, just to see if any differences have been made over it. And you can see the results are pretty comparable between those two tests really. So that's what the data looks like coming from the Fluke. You can see it does have both the pi and the DAR calculations in there, which is quite useful. And then these values here for the ohms, voltage and amps are actually at the 10-minute test point. Okay, so I've put those results into a spreadsheet and I'll show you that in the next screenshot. So these are the overall results obtained from the Fluke 1555. You can see these are my theoretical values here, and then these are each of the test voltages, with the final 5000 volt being done, the initial one, and then the retest at the end there. In the plot over here, I've plotted the 250 volt test and the initial 5000 volt test. And then the black line that you see almost splitting them in two is the theoretical. So that's pretty close. That's good enough for me. Quite happy with the result on that. Okay, so that ends this little video on the Polarisation Index Simulator. Hope you found it useful. Thanks for watching, and I'll see you again in the next video.